Hello everybody, welcome. Kevin Dennis here with Work at Height. Thank you for attending this webinar. It's titled Fall Protection by the Numbers. What we're going to do here is we're going to review numbers that you commonly encounter in fall protection to better understand the performance of fall arrest systems. My hope is that I explain these numbers in such a manner that you can go out into the field or out into your workplace, take a look at somebody and determine that they're going to be okay if a fall should occur in regards to force and clearance. Because all fall arrest systems have two basic performance requirements, whether it's a lanyard or SRL or lifeline or horizontal, all fall arrest systems have the two basic objectives. Number one, that's not to injure the person while arresting the fall. So it's a matter of force. I can injure somebody by having them fall into a harness just as easily as I can have them fall into the ground. So we have to concern ourselves with the amount of force that's involved in the fall. And then the second performance objective is to arrest the fall before the person strikes the ground or the next hazard. Okay, so it's a clearance issue. So all fall arrest systems, we have to concern ourselves with the force, and then we also have to concern ourselves with clearance. So I hope to explain this in such a manner that it hopefully makes it a little more simple. As in fall protection, there are a ton of numbers. All right, so the first number I would want to talk about is the arresting force. It's generally accepted that the human body, when wearing a harness, can safely sustain about 1,800 pounds. Tests that were done in the 60s and 70s, decades ago, determined that in and around 2,700 pounds, the human body is going to start to sustain injury. So obviously we can't go that high. We back off of 2,700 pounds, and OSHA, Washington, Oregon, California, Army Corps of Engineers, all of the regulators across the board say that no matter what you're using, you cannot expose a person to more than 1,800 pounds. So as the numbers go, for me, that's the starting point. Okay, that's the number I'd like to have everybody focus on, is that's the number that we can't expose that person to. So, sorry. This arresting force is a result when a weight falls a distance and is stopping. I apologize for my elementary little slide here, but it's a good way to explain it. And once I explain it, everybody's going to go, okay, this is very simple. We understand this for years, but every single piece of equipment operates on this premise. Okay? If I take a baseball and a bowling ball, and let's say the baseball is 10 ounces and the bowling ball is 10 pounds, and I drop them both the same distance. Let's say I drop them 5 feet onto concrete. That ball is going to hit with a force, and the bowling ball is going to hit with a force. But obviously the bowling ball is going to hit with more force because it's much heavier. Okay? So the arresting force is the result when a weight falls a distance and is stopped. Okay? If I change any of those variables, the arresting force also changes. Okay? If I drop the ball at a higher distance, if I drop it onto a foam pad, whatever the situation, anytime I manipulate the weight, the distance, or what it's stopping in, I can play with that force. So like I said, it's a pretty simple principle, but all of this equipment behind me, it all operates on that premise. All fall arrest systems operate based upon the weight of the object falling, so the person, how far it falls, the free fall distance, and how we stop it, the equipment that we're using to fall into. Okay? So the first number is arresting force, 1,800 pounds maximum. The next number is the weight that's falling, and that's basically the person. Okay? It's referred to as the capacity. And all equipment that's sold under the ANSI Z359 standards has a capacity range of 130 to 310 pounds. We don't have much influence over a person's weight. People are going to weigh what they weigh when they sign up for the job. Okay, but 130 to 310 pounds, that captures the vast majority of people that work up at heights. There are situations where you'll have equipment that can go under and some that can go higher, but that's a different webinar in and of itself of how do you go higher or lower or outside this weight range. But for the purposes of this presentation, the capacity or the numbers that we're using for the weight that we're dropping is 130 to 310 pounds. So going back to force, we know it's a relationship between the weight, falling a distance, and stopping. Let's take a moment and talk about the fall distance and the deceleration distance. So the free fall and the stopping distance, if you will. And the best way to understand that is bungee jumping. I have another picture here, and when this person jumps off this sky bridge, they're going to fall a certain distance until that bungee cord becomes tight. The distance that they fall before that bungee cord engages, that's the free fall distance. So free fall distance is the distance that somebody falls when there's nothing holding them back. They're picking up speed, they're accelerating. However you want to describe it, it's the distance where you're gaining momentum. Okay, the further somebody falls, the higher the energy potential. So free fall distances, regulators say that you shall not free fall more than 6 feet. And it's not the falling that actually injures somebody, it's how we stop them. Okay, so regulators putting a cap on the free fall distance is just an attempt to reduce the arresting force. Obviously, there are situations where you have to exceed 6 foot free fall distances. So you will actually see equipment that has a capacity, of up to 12 foot free falls. So I don't really need everybody on this call to remember all of these numbers. What I want you to remember about free fall distances is we want to reduce it as much as possible. The less distance somebody falls, the further ahead we are. There's less energy, there's less contact with structure, there's less chances of injury. There's just a whole lot of benefits to reducing free fall distance. All right, so going back to our bungee jumping here, once that bungee cord engages and it starts to stretch, that distance is all stopping distance. So anything that deploys, stretches, cushions, intentionally breaks or deploys, that's all good things. Deceleration distances vary considerably because the distance that's needed to decelerate depends on how much weight and how far the fall was. So you'll see products that have deceleration distances, anywhere from a couple of inches, to 5, 6, 7, 8, 9 feet, depending on how much weight and the fall distance. So I don't really need you to remember these deceleration distances, but recognize that it needs to be there and always work to increase it. Okay? Just like a car going down a highway, when you're on the gas, you're accelerating, that's your free fall. And when you go to slow down, you want to slow down over distance. You apply a brake, the softer the brake, the longer distance you need, the harder you brake, the shorter the distance. All of this equipment works on that same energy principle. So maximum forces, we know that we have to keep it under the body, are determined by paying attention to the capacity, controlling our weight, which again, we haven't got much influence on, but we can put bookends on it. Reduce the distance that the object falls, and then increase the deceleration distance, whether that's hitting the brakes harder, so we have more resistance in a shock absorber that deploys like 1,350 pounds, or applying that deceleration distance over time. All energy absorbers will have a resistance of either 900 or 1,350 pounds, depending on which product you're using. So it's really the energy absorber that saves the day in fall arrest systems. Okay, we haven't got much influence over weight. People are going to weigh what they're going to weigh. And we haven't got much influence over the free fall distance either. That's usually a function of the environment in which somebody's working. What structure do we have available to anchor to, and how much range of movement does somebody need to do the job? So we can manipulate free fall distances a little bit, but it's usually a function of the means and methods and the environment of the work. But energy absorbers are where we can really control forces. You'll see them on lanyards. You'll see them on personal SRLs. Inside of larger SRLs, there's a clutch or a screw or brake pads that will act like a drag on a fishing rod. The SRL locks up. If there's enough energy there, the drag engages, and that drag has a preset force that's not going to exceed 1,350 pounds. So as long as that drag is engaging, we've controlled the force to 1,350 pounds. And we'll also see the same thing on fall arresters, and even rope stretch on vertical lifelines is going to act as a decelerator. All right. So our first performance requirement of a fall arrest system is to control the forces. The easiest way to do that is through the use of an energy absorber through the product, as forces are limited as long as the energy absorber is deploying. I mentioned earlier that all energy absorbers, depending on which one you purchase, have a deployment force of 900 or 1,350, and that number is a constant through the full deployment of that shock absorber. What I mean by that is if a shock absorber only rips open, let's say 4 inches, it's ripping at 900 pounds. But let's say it rips out all 48 inches, all 4 feet of it, it's still ripping at 900 pounds. Okay? So if you're a lightweight person and you only fall, let's say 2 feet, so here's a graph that you can find in most manufacturers' instruction manual. User weight is down this side, fall distance is across here. Let's say I'm only 150 pounds and I fall 2 feet. I'm only going to use 6 inches of that shock absorber. Okay? So shock absorbers are equalize the force. Okay? Anybody within 130 and 310 pounds up to a 6-foot free fall, we're going to deploy different distances, but all of them are going to be 900 pounds of force. So that's the way in the field that you can safely predict the performance of the fall arrest system, is by using an energy absorber within its capacity. We don't need to be doing force over time estimates or any kind of calculations. Really, it's just, are we using that energy absorber correctly? Okay. The examples I just showed there were for a lanyard. The numbers change a little bit when you're using an SRL or a vertical lifeline or a higher capacity energy absorber, but the principles are the same. Is the weight and the fall distance within the capacity of the energy absorber, and that's where you can walk away feeling pretty good that the forces on the person are going to be below acceptable levels. So that's how we predict forces, is using energy absorbers within their capacity. The next number I wanted to mention is minimum braking strength. We read the minimum braking strength probably more frequently than we do any other number in fall protection. Anchors have to be 5,000 pounds, anchorage connectors 5,000 pounds, snap hooks, carabiners, D-rings 5,000 pounds. So just due to the frequency of us reading braking strengths, all too often people tend to focus on the braking strength rather than focusing on the force. So braking strength is necessary. It's obviously numbers we have to pay attention to, as we want to make sure that the equipment isn't going to break as we're using it. But the first number I would encourage everybody to focus on is the force on the user. Okay. I'll give braking strength here. It's an explanation on the slide here. But if I take a carabiner and I start pulling on it, it starts to stretch. And then eventually, if I keep pulling on it, like if I'm going to take it to failure, it will start to bend and deform. Then it'll really start to bend and deform. Then ultimately, it'll just break. This number right here, when I go and test 1,000 carabiners, whatever the common number there is that all of the carabiners are higher than, that can be my minimum braking strength. So if OSHA says your carabiner has to have a minimum braking strength of 5,000 pounds, a manufacturer will make 10,000 of these. They'll test 100 of them, and as long as they all break higher than 5,000 pounds, they can safely assume that all of those carabiners are good and the design's good, and you're putting it out with a minimum braking strength of 5,000 pounds. Okay, so braking strength is quite understood, but it's when something actually fails. So the braking strength that I want us to pay attention to is the braking strength of the human body, which we know is going to be in that above 1,800 pounds is when we're into a danger zone, is when we're up here with a human. So braking strengths and all of the numbers that you see for braking strengths, they're necessary, but they don't affect the force or the clearance. It's a quality number to make sure that the equipment you're using is going to be strong enough to sustain the forces of a fall, and it's overbuilt enough so that it's got some life to the product. Okay? You know, in reality, all of this equipment is only ever going to realize 1,800 pounds. And in truth, if we're using the shock absorber correctly, all of this equipment will actually only see the arresting force of 1,350 or 900. Okay? So although 1,800 is our upper limit for a person, we can actually do a little better than that of getting it down to 900 or 1,350 through the proper use of the equipment. So braking strength numbers, you know, anchorages and anchorage connectors 5,000, lanyards 5,000, SRLs and rope grabs 3,600, harnesses are 3,600 or 5,000 depending on the year you bought it. But I'd tell you, we don't braking strength numbers are a purchasing problem. Okay? You don't in the field pay attention to the braking strength of something. You do when you buy it. This is what we should concern ourselves with in the field, is how we're hooking all that equipment up. How do we control force? We pay attention to the free fall distance and the user weight. All right. So weight, free fall distance, and deceleration distance is always controlled here by this equipment in the middle. Okay? The harness and the anchorage really don't play a part in free fall distance and deceleration. Okay? The anchor plays a little part in the free fall distance depending on where it is, but you know, the harness is really focuses just containment, anchor is strength. All of this equipment has to be strong enough to hold, but in the field, to know that we're hooking up safe systems, pay attention to that energy absorber. Okay? All right. So looking back at our second performance requirement of fall arrest systems is a matter of clearance. We have to arrest the fall before the person hits the ground. We know how to control force. Okay? It's through the use of an energy absorber within its capacity. And now we just have to look at how far is the person going to travel. So in any training event that I do, I spend a lot of time on clearances. Everybody usually incorrectly assumes that all equipment is the same, all SRLs only need 5 feet of clearance, all lanyards need 18 feet of clearance. And although those are good general statements, when you actually look at the application, there are thousands and thousands of different scenarios where the clearances are all going to change. Okay? So I'll give you an example, and what we know now about this equipment, we could predict the performance of fall arrest systems. Okay? So I've got my little graphic here. I've got a 180-pound person. They've got a 6-foot lanyard anchored 2 feet above their head, or sorry, above the back D-ring, and they have a 6-foot FF energy absorber. Okay? So we know how to control force. The capacity of the 6-foot FF energy absorber is a 310-pound person with a 6-foot free fall. Okay? At those numbers, there's going to be a 900-pound average arrest force with a 48-inch tear out. Okay? So really, all I have to ask, I don't have to do any calculations in the field. I just have to say, am I using the shock absorber within those parameters? So looking at my situation, that person is going to free fall 4 feet. There's 4 feet of slack in that 6-foot lanyard, okay, since it's anchored 2 feet above his back D-ring. So I now know enough to predict the force. Okay? I've got a 180-pound person free falling 4 feet. It's well within the capacity of that shock absorber. I know that the force on this person isn't going to exceed 900 pounds. So I've accomplished, or I can safely assume that my first performance requirement of stopping the fall within acceptable forces has been met. So the next objective of the fall arrest system is clearance. So we also know enough about this equipment that we can predict how far this person is going to travel. That line is a fixed length. That's only a 6-foot lanyard, so it's going to do a hard stop right here, and then that shock absorber is going to begin to deploy. It has got a total of 4 feet in it, recognizing that I'm not going to use all of it. I'm only going to use a few inches of it. If I really wanted to, I could get a little more accurate of going to the user instructions and go, 180-pound person is right here. We've got a 4-foot free fall. We're going to use about 15 inches of deployment of that shock absorber. Now in the field, I don't expect anybody to go and open up instructions and cross-reference charts, but if you're doing job planning or you do have an application where you have some pre-planning time, you can certainly do that. In the field, most everybody just takes that full deployment. If nothing else, the estimate's going to be conservative. So there's nothing wrong with that. It just depends on how accurate you want to get. Once that shock absorber deploys, the harness is gonna collapse around the person's body, D-ring slides. Everybody typically gives a foot for that harness stretch. Since that person was anchored in their back D-ring, we have an additional 5 feet for the consideration of their body, and then a 2-foot factor safety. Okay. The numbers in fall protection, everybody assumes everybody is 6 feet. Okay, and that D-ring is anchored at the 5-foot level from their feet. So those are a little fuzzy, if you will, fuzzy logic. So people are obviously different heights. But for estimates, we just take everybody being 6 foot, 5 feet to the dorsal D-ring. That's one of the reasons there's a factor of safety and everything. These estimates that we give for clearances, they should be overly conservative. They should be excessive, okay? Which they are because of our factor of safety, and we're assuming full deployment of that shock absorber, knowing that it's not going to deploy fully. So in this application, in this environment, that anchor point needs to be 2, 6, 10, 11, 16, 18 feet off the ground. So I can look at the equipment, look at the performance of it, and now compare that 18 feet to the environment that I'm working in, that I know I'm going to be okay in regards to clearance. And I can do the same thing with self-retracting lifelines. Okay. Again, they all have a performance standard that they have to meet, and the manufacturers provide those numbers. And SRLs are actually easier because all of the numbers supplied by the manufacturers include harness stretch, factor of safety, worker height. All of the numbers are included in those graphs that have to be supplied with them. So in this application, I have a 240-pound person with a class 1 SRL. It's directly overhead here on our chart. I only need 5 feet of clearance below that working surface. And that 5 feet includes the margin of safety and harness stretch. So you could back out of those numbers, you know, if you really are interested, there's my 2 feet for my factor safety, 1 for the harness stretch. This SRL would lock, the free fall and deceleration distance will occur in 2 feet or less. Okay. We can do the same thing with self-retracting lifelines for leading edge applications, class 2 SRLs. The challenge with these is that there's always an additional 5 feet worth of energy. When somebody's standing at an edge, since the anchor is at foot level, I've always got 5 feet of extra energy to deal with. So you will see increases in the clearances. You will see the addition of a external shock absorber as well as the internal shock absorber, and that's to handle this extra energy and the problems that this edge creates. The forces on this system, since we introduced this edge here, is the forces on the downside of the edge are going to be different than the forces on the upside of the edge. So therefore we need to put a shock absorber at both locations to save the cable and the person going over that line. So the numbers just increase, but it's still a weight, distance, and deceleration. We know what we know now about a resting force is when we increase this free fall distance, we have to increase the deceleration. That's why you will see larger shock absorbers on class 2 SRLs. So looking at the instructions with no offset and a 6 foot setback, I need 17 feet of clearance from that walking working surface. But I know my person is only 180 pounds. It's well under the 310 capacity of the SRL. And as long as my environment has the 17 feet, I'm good on the second performance requirement as well. So estimating clearances ensure that a person won't contact the ground or the next hazard, and that is the second performance requirement. So knowing a little bit about the numbers, the 1,800 pound maximum arresting force is controlled or monitored, if you will, by the weight, the free fall distance, and the use of an energy absorber and deceleration distance. And then the clearance is just adding up all of the factors that increase distance. So you have to know a little bit about the equipment. You have to know how it performs, how it deploys, how it stretches, but none of this is very difficult. The challenge is that there are thousands and thousands and thousands of different applications. So thank you very much, everybody. Hopefully I explained it in such a manner that it didn't confuse the group further, and that you're able to go out into the field and take a look at your fall arrest systems and determine that they're going to be okay in both in regards to force and the amount of clearance that they need. So let's take a look at the chat and see if anybody has questions.